Okay, so 1.3, you're going to feel very reminiscent of your pre-calc stuff. So it is nothing but reviewing how we transform functions and relate them back to their parent graph. And it does touch upon some function composition stuff. So this is just review. So you're going to notice the first few sections, they're going to be review. So let me remind you of some rules here. So if we have a parent function f of x, and if we add on the outside, it's going to shift it up. If we subtract on the outside, it's going to go and move that function down. So you can just highlight if there's not much really for you to write in. Remember, if you subtract on the inside, it's going to go to the right. And if you add on the inside, it's going to go to the left. So I talked about that stuff a lot last year. And you might recall some of the homework and the assignments you did in Alex related to those very topics. So there are those fundamental rules from pre-calc continue into this course. You know, you obviously, I didn't just teach you that stuff for the heck of it. So let's take a look at example 1. So if we have the parent function y equals x squared, what does that graph look like? Parabola. And what are the points? What are some of the points that we can put? What if we went all the way to 2? If we plugged in 2, what are we going to get? If we plug in -2, what are we going to get? Okay, so let's take those 5 points and let's transform them each time. So this first one here, the function f of x plus 1, what is that going to do to our original function? If we add on the inside, Alex, what's it going to do? It is going to go to the left. So that's why we need to remember those rules. So please make sure you look over that page and remember, where is it sitting? If it's on the inside, it is going to move how the x has changed. So in this particular one, it's going to move it left one. So let's take all of those points and just shift them to the left one. Okay. Yeah, mine's beautiful. The second one here, where we have f of x plus 1, what happens to that one? It goes up 1. So let's take the original red function and move all those points up 1. Our third function, I'm going to make that one in kind of a green color. The f of the quantity of x minus 2. It's going to go right 2. So let's take our original red function, our original parent x squared, and let's move each point to the right 2. But these are not transformations or any kind of dilation. The exact shape of our graph and the distance apart between points in our graph, they do not change. And then finally, our last one here has a subtraction of 2 on the outside of the function. What's going to happen to that one? It's going to go down. So let's take our original function and move it down. There are. I try to at least change color, although my projector doesn't. You can't see much difference between the pink and the purple, but those should be things that are easy for us, and we should remember those things. If you've forgotten those rules, take a look at that page that has those rules on it. Remember, if we add on the outside, it's going to go up. Subtract on the outside, going to go down. Add on the inside, we'll move left. Subtract on the inside, we'll move right. So just make sure you remember those rules, okay? Everybody good with example 1? Okay. Some other things about stretching and reflections. If we have a value that is larger than 1, and I'm thinking of the absolute values larger than 1, if it's on the outside and it's larger than 1, it will stretch up the original graph. So you could think of it stretching up. If you have 1 over that, so that would be a proper fraction in front, it's going to compress it down. So if we put a 2 in front of our x squared, it is going to raise it by a height of a factor of 2. But if we put a 1/2, it's going to compress it down closer to the x-axis. And that vertical stretch, always think, how does it relate to the x-axis? Now, the ones that are always weird are the horizontal changes. Anything on the inside of the function does the opposite of what your brain wants it to do. So in this particular case, if we have a number by our x that is more than 1, so if we're thinking about if we put a 2 by the x, it will actually compress it inward. And let's put the word inward. So the top thing moves it up and down because it's vertically moving it. The horizontal, it changes it from left to right, but you can think of it inward and outward. In and out. Okay. So if we, and this, can we change this to x over c? So ignore what it said. If you have x divided by a number like x over 2, x over 7, x over 4, x over 3, it is actually going to stretch the graph outward. It is going to stretch our graph outward. So it's going to move it away from the y-axis. Because it's a horizontal change, it changes how far away from the y-axis it is. I think of a slinky. If we have a sine function that we have made into a slinky, if we put a 2 by our x inside the sine function, it's going to push our slinky in. If it has like an x over 2, we put that into the sine function that made our slinky, it's going to pull our slinky outward. So if you think of it like a slinky moving in and out, or a spring going in and out, that's a helpful way to consider how we have a compression or a stretch that's going horizontally. Think of a wave going this way. For vertical stretch, I always think of, think of a parabola if it has strings on it and you're pulling it upward or you're loosening the strings. It's that's a good way to think of a vertical stretch. And then lastly are the reflection stuff. If you put a negative on the outside, it reflects it about the x-axis. If you put a negative on the inside, it reflects it about or over the y-axis. Okay, so those I will remind you as we go, but the more that you can recognize quickly what happens to a function, the better you're prepared to graph it quickly. Because that's our goal. When I was going over graphing last year, one of the main goals that I hoped occurred is that you were faster at graphing than you were in an Algebra 2 course. That you came out of pre-calc and looked at the equation and go, oh, that's this, I can do this, that's the way it's graphed. Because in calculus, the graphs will be helpful, but there's math after that. So if we can graph the things quicker, it'll make our life easier as we go. So now let's look at this particular example. So it's still that same parent parabola, so let's put that on there. So I'm going to put my original parabola up there. And I am going to do the ones that have something on the outside first. So let's do those first because those are the easiest for us to contemplate how it works. Okay. So let's do 2 times f of x. Now this should stretch it upwards by a factor of 2. So the distance away from the x-axis will double. So that's pretty easy to do. This one will be at a height of 2 now. This one will be at a height of 8. So the distance from the x-axis has doubled. This one, no, not that one, I'm sorry. This one. That is going to change the distance from the x-axis. It is going to compress it down. So now we will be half the distance we were before from the x-axis. So if we take the points, this had a distance of 1, now we'll be at a half. 0, 0 is still 0, 0. This has a distance of 4, now it'll be at a distance of 2. So the distance from the function to the x-axis has decreased and been cut in half. So on the outside is a little bit easier for our brains to comprehend. It just is. Okay, now let's take a look at the 2 that are a little weirder. This first one here, f of 2x. The 2 inside is going to compress it inward, okay? So now we have to take those points and we have to relate it to the y-axis. So it is going to half the distance to the y-axis, okay? So let's zoom in. Let me zoom into the red function. And then we're going to compress those points closer to the y-axis, okay, by half. So this was 1 away from the x-axis. Now it's going to be a half away. Or from the y-axis, I'm sorry. This was 2 away from the y-axis. Now it's going to be 1 away. So that's what a compression looks like if we put a 2 next to the x. It smashes the distance from the y-axis. This one. It is going to stretch it out away from the y-axis. So we're going to take the red points and we are going to double the distance away from the y-axis. It is always the reciprocal of the fraction that was under it, or if you're divided by 2, you're going to really multiply those distances by 2. So this was the distance, so it's normally 1 away. Now it's going to have to be 2 away, so here and here. This one here was 2 away. How far away are we going to have to be now? 4 away. Now, worst comes to worst, we know how functions work. We could have plugged in x over 2 into the function. We would get x squared over 4, which would have done the same exact thing. So you have a function to work with. The problem is you may not always have that actual equation there to work with. But if you have an equation to work with, feel free to plug anything into the equation, because remember, you got to remember here that the algebra and the graph should always go together. If they don't go together, one of them's wrong. Which one's wrong? What did you do wrong? Okay. Everybody good with those ones? Stretches, compressions are weirder. Last year we avoided them a little bit. I mean, we talked about them, but I didn't stress them because they're just harder than the other things. Okay. And then this one, we want to find the functions that do the following. We want to actually find the function, and then we'll graph it. So let's put our parent function again in red. So we'll call this one A, and this one B. For A, if we want to reflect about the x-axis, we want to flip it over the x-axis, we would put something that moves it up and down is always on the outside of the function, so that would be negative f of x or negative x squared. So we know what that does. That looks like that. Okay. For B, we want to reflect something about the y-axis. For that to happen, we're going to put it on the inside. But what's interesting about this function, and it doesn't always happen, but it could, since this function is an even function, we've learned from symmetry that the negative x plugged into a even function will always result back to the original version. And think about it. If I flip this point over the x-axis, it's going to go over here. I'm sorry, the y-axis. If I plug this point or flip it over the y-axis, it's going to go over here. So I end up just being an exact duplicate of my original. So if you want to change the function somehow up and down, you do something to the outside of the function, because that's going to affect the y values. If you want to change the function somehow left to right, you do that by doing something to the x's on the inside of the function. And if you remember that, that will help guide you as you go through the process. The inside of the function is always the one that's the most strange to contemplate. The outside of the function just kind of feels like it should feel. It just kind of works. Everyone good with example 3? Okay. So let's practice graphing. So you need to be able to graph and graph quickly. If I were to see a quadratic in its trinomial form like this, that x squared plus x plus a number, I would always graph it by finding the vertex as x and do negative b over 2a. That's the most efficient way to do that. So in this case, our a value is 1 and our b value is 6. So that would be negative 6 over 2 or negative 3. And I would do an old-fashioned plug in the vertex, plug in something to the left of it, something to the right of it, get my 3 points, make my parabola. You should know right off the bat, hey, that's a parabola. I don't know what the vertex is. I can do negative b over 2a at any time, and I can find the vertex of my parabola. So if it's in that quantity of something squared, you can find the vertex very easily if it's completed the square, but this hasn't been completed. That's the quickest way to do it. If you plug in negative 3, you get 9 minus 18 plus 10, which is 1. If you plug in negative 4, you get 16 minus 24 plus 10, which is 2. If you have chosen the correct vertex, negative 3, 1, negative 2 should also result in the exact same value, or you have not chosen the correct vertex. We have chosen correctly. We did get the symmetry happening. We got the correct values. So now it's just a matter of graphing. So for this one, we're going to start at -4. We're going to go up 2. If we plug in -3, we get 1. If we plug in -2, we get 2. You can easily plug in 0. If you plug in 0, we do get 10. That's just a nice way to really have an accurate parabola. So we get a parabola. Okay. Part B. What's the general look of this function, the square root of x minus 2? Anybody tell me? Swoosh to the right? Okay. You should know that. What is the x minus 2 going to do to our swoosh to the right? It's going to move it to the right. How many units? 2. So if you know that the original goes 0, 0, 1, 1, and then 9, 3. I don't know why I went to 9, 3 instead of 4, 2, but anyway, you can take those points. I was just jumping the gun there. And we can move them over. So if we jump, this would be the starting of the swoosh. This, if you plug in 3, you do get 1. If you plug in 4 away, 1. If you plug in 6, you do get 2. So you can also say, where will that equal 0? Oh, it's going to equal 0 at 2. Where will it equal the next perfect square? The next perfect square is 1. That's going to be at 3. And where does it equal the next perfect square, or 4? That's going to be 6. So I would plug in 2, 3, and 6. You're going to get 0, 1, and 2. But all of those graphing techniques that we learned last year, you still have to know. Pre-calc is a thing so that you're prepared for this class. So hopefully last year prepared you to get to here, okay? So that's example 4. Do we have any questions about that? Okay. Yeah, there's lots of ways to graph it. So whatever technique you like, there you go. Oh, look at this. The cosine graph. The main thing you want to remember when thinking of the graph of the cosine, guys know it's a wave. It starts at 1 and goes down to 0 and then -1, does a cosine start at 0 or does a cosine start at 1? So think on the unit circle. Does the cosine value at 0 degrees, is it 0 or is it 1? The cosine of 0 is 1. So we know that, let's make this 1 and make this -1, okay? We know that the cosine of 0 is 1, and then just follow your unit circle to get the first wave. It's got to come down. At pi over 2, it's 0. At pi, it's -1. At 3 pi over 2, it's 0. Back around to 2 pi, it's 1. So that is one period of our cosine graph. In this class, very rarely are we going to graph anything besides a sine or a cosine. I very rarely have seen a tangent graph or any of the other funky graphs. It seems to be sines and cosines that we have to rely on most. I think possibly if you took in your future, if you take a Calc 2 or 3 class, where some of the reciprocal ones, that the tangent, the cotangent, secant, cosecant will pop up a little more often. So let's make the full graph. Okay, so now we're going to use our rules of functions. For example, B, what does it do to a function if we have a 2 on the outside? It stretches it up, right? For this, it wasn't actually, we gave it a name. We called it the amplitude. So the amplitude of this cosine wave became a 2. So now we're going to go up to 0, down to 0, up to. So we just stretch it upward. We should expect that happens for the stuff we learned in trig, and just every function, if you multiply by a number bigger than 1 on the outside, you will always stretch it away from the x-axis. Beautiful, right? Now, what the C does is it compresses the distance to the y-axis by a factor of 2, or it cuts it in half. Okay. So if this is 2 away from the y-axis, now that distance is 1 away. Now, if you're touching the y-axis, you're just going to stay there. That's why it goes like that. Now, remember, every up and down are equally spaced. So now that we have one bump up, we know where the other bump is down. But let's just verify. This is 4 spaces away. So half of 4 is 2. So now it's only 2. This is 1, 2, 3, 4, 5, 6 away. Now it's only going to be 3 away. So it did make a bump in the time we expected it. And then once you have a full up down, just repeat. They always have to be equally spaced. So don't overthink it. So this is going to go up and down for the rest of its little life. I'm such an amazing cosine grapher. But that's how we would graph that one. Now let's talk about D. For D, I would suggest a little rewrite because it's hard to see, but for function D, we've actually made 2 transformations. So I would do a little rewrite to this. I would write it as the negative cosine of x plus 1. I would put the 1 on the other side and think of order of operations. The first thing to touch it is a negative on the outside of the function. What does the negative on the outside of a function do? What does a negative on the outside of a function do? Anybody remember? It makes it flip across the x-axis. So the first thing I want to do to my red original function, I'm just going to flip it, okay? So then we have something to work with. So let's just flip the red one. So it's going to look like this. And I'm going to make it dashed because that's not my final answer. And that will just help me. I just took the red function and I just flipped it over. Okay. So I just took the red function and I flipped it over. That is if we wanted to graph y equals negative cosine of x. What's the plus 1 on the outside of the function do to the function? Moved it up 1 unit. So now just to finalize our final answer for part D, we're going to take all of the major points in the purple dashed function and we're going to lift it up 1 unit. So this would be up here. This would be here and here. Find yourself 1 bump and make it. And then this one is going to be here. This one's going to be here. There's an upper bump. As soon as you see the upper and lower bumps, it becomes much easier to complete the process. Maybe you can't see where all this is at. There's too many graphs on. So this one's here. This one went up to here. This one went to here. So look what I did. I don't understand. So all I did was took this point, moved it up 1, up 1, up 1. So you can see that my one in the dashed purple has just taken every one of those points and slid it up one. So this is your final answer. Kind of makes sense a little bit? Are we running out of time? Yeah. So we'll stop here. We'll finish these tomorrow. So there you go.